Hello, my name is Jan van Waarden and I would like to talk about cosmic ray acceleration in oblique astrophysical shocks using combined particle-in-cell and PIC-MHD simulations. This is something I've been working on together with Alexander Markovic at Laboratoire Univers des Particules de Montpellier and in collaboration with Artem Bodan, Martin Pol and Paul Morris at the Deutsche Elektronensynchrotron. It is generally understood that astrophysical shocks are capable of accelerating charged particles to relativistic speeds through a process known as Fermi-1 or diffusive shock acceleration. These particles can be observed on Earth as cosmic rays. This process is both self-induced and self-sustaining. The presence of non-thermal particles triggers instabilities in the upstream magnetic field. These instabilities then reflect particles back toward the shock, which accelerates the particles further. Because the wavelength of the instability scales with the current, the instabilities grow to match the energy of the particles as the particles gain speed, meaning that the process will continue. The question is, what do we need to model this computationally? On the one hand, we're looking at very large-scale structures, the astrophysical shocks, which can vary from an astronomical unit to more than a megaparsec. On the other hand, the process itself involves microphysics, which happens on a very small scale. This brings us to two very different computational methods: magnetohydrodynamics, also known as MHD, and particle-in-cell, also known as PIC. Magnetohydrodynamics treats a plasma as a fluid. It defines the plasma in terms of statistical averages, such as mass, momentum, and energy density. This method is very good at large-scale simulations. It's computationally efficient, but it cannot simulate microphysics. On the other hand, the particle-in-cell method treats a gas as a collection of individual particles. This means that it can simulate microphysics and can simulate a non-thermal plasma, but it's computationally expensive, which is a problem when you try to model a large-scale structure. It also tends to be numerically noisy. Ideally, we want to combine the best aspects of both: the large-scale efficiency of the MHD method and the ability to simulate microphysics of the PIC method. This is possible using what we call PIC-MHD. PIC-MHD rests on the assumption that an astrophysical plasma can be treated as a combination of two plasmas: a thermal plasma, which can be treated through MHD, and a much smaller non-thermal component that has to be treated through particle-in-cell. In practice, a PIC-MHD code works by defining a single grid. At the cell centers of the grid cells, we define the quantities of the thermal plasma in terms of mass density, energy density, momentum density, and magnetic field strength. At the same time, the grid contains individual particles which represent the non-thermal plasma. At the start of each time step, we look at these particles and use their position and velocity to define a current and charge density at the center of each grid cell. Using this, combined with the characteristics of the thermal gas, we then update the characteristics of the thermal gas through the conservation equations of MHD. This gives us a new electromagnetic field at each cell center. Using the electromagnetic field, we can then move the particles using a borders pusher. This gives us a new spatial and velocity distribution for these particles, which allows us to define a new charge and current density at the cell centers, which we can then use in the next time step to update the MHD quantities. We now wish to investigate the influence of the obliquity of a shock on the diffusive shock acceleration process. Hybrid PIC simulations done by, for example, Caprilli and Spitkowski in 2014 and Hegarty and Caprilli in 2019 showed that if the magnetic field made an angle of more than about 60 degrees with the flow of the upstream gas, no magnetic field amplification or particle acceleration occurred. When we tried to do the same simulations using PIC-MHD in 2018, we found that both could happen, owing to long wavelength instabilities that couldn't be captured by the initial hybrid PIC simulations because of the scale of the simulation box. However, these PIC-MHD simulations do not actually model the internal structure of the shock, because the shock is treated through MHD and is therefore a discontinuity. Instead, PIC-MHD relies on an ad hoc description of the injection rate of non-thermal particles at the shock front. And in 2018, we used injection fractions identical to those of parallel shocks. In order to improve on these results, what we need is a two-stage approach. We need to use a PIC code to determine the injection fraction, and then use that injection fraction in a PIC-MHD code to follow the long-term evolution of the gas. In order for the reflected particles to be able to trigger instabilities in the upstream medium, the energy of the reflected particles has to be bigger than the energy of the upstream magnetic field. And in order to determine whether this was even possible for shocks at high obliquity, Artem Bodan ran a series of PIC simulations in 2D where he varied the obliquity angle between 45 and 70 degrees. And he found that the injection rate decreases very rapidly. If we look at the graph, then we can see that at 45 degrees, the injection energy as a fraction of the shock energy is close to 10%. If we go to 60 degrees, it is down to somewhere between 1/10,000th and 1,000th of the shock energy. And by the time we reach 70 degrees, less than 1/1,000,000th of the shock energy is reflected back upstream. The reason is that if the obliquity is high, only very fast particles can move upstream at all, which means that only a small fraction of the particles is actually able to move back upstream. In the same plot we show with the green curve the critical alphanic Mach number. This is the alphanic Mach number at which the magnetic field energy in the upstream medium is below the energy of the reflected particles. And as we can see, at 45 degrees, that means that an alphanic Mach number of about 4 is already enough. At 60 degrees, you need an alphanic Mach number of about 50. And at 70 degrees, you need an alphanic Mach number of about 1,000. So, at least in theory, it is possible for oblique shocks to have instabilities in their upstream medium, but only at relatively high alphanic Mach numbers. As an example, we look at the shock at a 60-degree angle. For that, we find that approximately 5 times 10 to the minus 5 of the original particles is reflected back upstream. And we use that number to start a series of PIC-MHD simulations. For the PIC-MHD simulations, we take a large-scale two-dimensional box in order to be able to capture longer wavelength instabilities. And at the shock, we inject the particles at a rate of 1 times 10 to the minus 4. Note that this is twice as much as found by the PIC simulations. However, in the PIC simulations, we only counted particles being reflected upstream. In PIC-MHD, we inject the particles isotropically in the rest frame of the downstream medium. And that means that we need to inject twice as much in order to get the correct number of particles moving upstream. We kept the obliquity fixed at 60 degrees, kept the gas parameters of the thermal gas constant, except for the alphanic Mach number, which we varied between 20 and 300. The resulting spectral energy distribution for the particles is shown in this graph. As you can see, for the two simulations with an alphanic Mach number of 20, the dashed red line and the green line, we find effectively no diffusive shock acceleration. The particles are accelerated, but this is only due to shock drift acceleration at the shock front. There is no high energy tail to the spectrum. However, if we look at an alphanic Mach number of 50, the dark blue line, we see that there is a high energy tail, albeit a relatively small one. This indicates that diffusive shock acceleration is beginning to take place, as was predicted by the PIC simulations. If we make the alphanic Mach number even higher, 100, the purple line, 300, the light blue line, we see that the high energy tail starts to extend further and further to high energy. And at 300, we even begin to see a plateau between gamma minus 1 being approximately 0.04 and 0.1. This indicates that the diffusive shock acceleration is beginning to become efficient. Now we'll take a look at the characteristics of the plasma. As an example, here we show the result for the simulation with an alphanic Mach number of 300. In the top panel, we see the magnetic field strength relative to the original upstream magnetic field, as well as the magnetic field lines. In the center panel, we see the particle density of the non-thermal particles relative to the particle density of the thermal particles. And at the bottom, we see the gas density of the thermal plasma relative to the original upstream gas density. What becomes very clear is that the disturbance of the magnetic field is small. Both the magnetic field amplification and the distortion of the upstream magnetic field are barely noticeable. And this means that you will always need a large simulation box, because otherwise particles moving upstream may well escape through the upstream boundary before they can be reflected back at the shock, in which case you're not going to see any acceleration at all. To conclude, our PIC simulations show that the injection rate of non-thermal particles decreases very rapidly for shocks with an obliquity of more than about 50 degrees. We do find through our PIC-MHD simulations that particles can trigger the streaming instability in the upstream magnetic field, but only if the energy of the upstream particle flow exceeds the local magnetic field energy. This means that for an oblique shock to be able to trigger the streaming instability and thereby trigger diffusive shock acceleration, a high Alfvénic Mach number is required. Our simulations find that at 60 degrees we need an Alfvénic Mach number of more than about 50. And our prediction is that at 70 degrees you would need an Alfvénic Mach number of more than about 1000. And with that I conclude my talk. Thank you very much for listening.